Welcome to the deep dive. We're launching into a really fascinating exploration today. Chemical rocket propulsion.
Yeah, it's quite a topic.
You sent us a great collection of materials, scientific papers, technical reports, all sorts. Our goal here is to pull out the key knowledge, the core insights, just for you.
Exactly. Think of it as a guided tour
Through everything from, the basic science of how propellants
to
burn.
the really cutting edge stuff like greener rocket tech.
So we've got a pretty diverse set of sources to work with.
We really do. Looking at the energetic materials themselves, solid propellants, liquids, hybrids.
Safety aspects, environmental impact too.
Right, and even some history, how we got here. Our mission really is to synthesize all this, make it clear, engaging, and highlight what's most important for you.
Yeah, sounds good. Let's jump right in. The heart of it all. Energetic materials and propellant combustion.
The fundamentals.
One thing that really jumped out from the papers is how much metal combustion affects propellant ignition and burning.
Oh, absolutely. It's a huge factor.
Yeah.
When you have metal particles burning inside the propellant,
Yeah.
well, the type of metal you use, how much of it is in there that directly ties into how fast the propellant burns.
That's how sensitive it is.
Exactly. To changes in temperature, changes in pressure, it's all linked.
Okay. Now, the research also brings up something called two-phase flow loss. Sounds like a performance killer, especially with these metallized solid propellants.
It definitely can be. It's a major challenge.
What's the basic idea?
Well, think about the exhaust. When these propellants burn, you don't just get gas, you also get tiny solid particles or even liquid droplets.
Ah, okay. Two phases. Gas and condensed stuff.
Precisely. And having that mix flow through the rocket nozzle isn't as efficient as just pure gas. There are losses.
What causes it?
It's complicated. It's partly the combustion happening right near the propellant surface, and partly how that mix of gas and particles behaves dynamically as it squeezes through the narrowest part of the nozzle, the throat.
So it's a combination of chemistry and fluid dynamics.
You got it. And while we have some, let's say, rules of thumb for older conventional propellants,
Yeah.
these newer high-energy formulations, we still need to study them more to really understand and minimize this loss.
Is there a general strategy?
Generally, the advice is to try and reduce the amount of material that ends up condensing into liquids or solids near that burning surface. Keep it gaseous if possible.
Makes sense. Keep the flow clean. Now, shifting gears slightly, one paper mentions the EM Genome Initiative, EMGI. Sounds pretty ambitious.
It really is forward-thinking, EMGI. It's about understanding energetic materials right down at their fundamental microstructural level.
Like finding their DNA.
Kind of.
Yeah.
Identifying the basic genes, these microstructural features that dictate the material's overall properties, its performance, its sensitivity, everything.
Wow. So if you crack that code.
The idea is you could potentially design and manufacture new energetic materials much more efficiently, almost engineering them from the atoms up for specific tasks.
So you identify the key ingredients at the smallest scale to get the big picture properties you want. What are some examples of these EMGs?
Well, the sources give a few. For instance, at the molecular level, things like having flat, interconnected structures, or strong hydrogen bonds holding the molecule together internally, or strong chemical bonds that are just hard to break. These often correlate with lower sensitivity to shock.
And how they pack together.
Yeah, in the crystal structure. Strong hydrogen bonds between molecules, helping them stack neatly. That's another important factor mentioned.
But finding these links sounds like a huge challenge.
It is. The source makes that clear. Finding these fundamental genes requires massive amounts of data. You need to build, essentially, a giant database connecting the tiny micro details to the macro behavior.
A monumental task indeed. The research also touches on some really advanced material synthesis, like core shell structures, using atomic layer deposition, ALD. What's that about?
ALD, yeah. It's a technique that lets you deposit incredibly thin, uniform coatings onto tiny particles, layer by layer, almost atom by atom.
So super precise coating.
Extremely precise. The example given is an aluminum core coated with a thin shell of tin dioxide. The images in the source really show how uniform it is.
And what's the benefit?
Well, it can create new materials with tailored properties. But what's also fascinating is using ALD to improve existing materials.
How so?
Like, the research mentions coating zirconium nanoparticles with aluminum oxide. This stops the zirconium from oxidizing in air, which would normally degrade its performance.
Ah, protective layer.
Exactly. And another example was coating AD and ammonium dinitramide to create a barrier against water molecules. Makes it more stable, especially in humid environments.
So it's like high-tech armor for nanoparticles.
Okay, let's zoom out a bit. The sources also really stress looking at the whole life cycle of these propulsion systems. It's not just design and launch.
Absolutely critical. If you want to manage the risks involved with energetic materials effectively and do it cost efficiently, you need the complete picture.
Right.
From understanding the basic material properties to how it's made, how it behaves in service, and importantly, how you dispose of it safely at the end of its life.
Right, is the cradle-to-grave approach.
Exactly.
And when we talk about the big challenges in rocket propulsion generally, what are the key areas?
Well, the sources cover general issues that apply to pretty much all launch vehicles,
Mm.
but they also dive into specific concerns for solid rocket motors, SRMs, the ones using solid propellant.
And liquid rockets?
Yeah, there's a separate section on liquid propulsion we'll get to later on.
Okay. Now, Europe seems particularly focused on mastering the tech for these large, single-piece, solid rocket boosters, like for the Ariane launchers. What's the deal with those?
They're known as monolithic SRBs, essentially very large solid boosters made as one continuous unit.
And they use some advanced stuff.
Oh yeah, we're talking graphite composite casings for strength and low weight, special EPDM rubber for insulation, flexible seals, flex seals to handle nozzle movement, high-temp carbon materials inside.
And then the propellant itself is often a high-performance type based on HTPB binder, usually with a complex internal shape called a phenol grain to control the burning.
So the European focus is on perfecting the whole package.
Right. Mastering the technology and the manufacturing processes to build these big, powerful boosters reliably.
We also see mentions of progress elsewhere, right? India with large boosters, Europe upgrading its smaller VGA launcher, Japan working on reusable liquid engines.
Absolutely. It's a global effort. The papers you sent give a snapshot of different approaches. India's successes, VG's performance bumps, JIXA's push towards reusability, different regions, different priorities.
It shows there's innovation happening all over.
Definitely.
Okay, let's explore a really crucial area now. New energetic materials, particularly ones that are more eco-friendly. That green aspect seems more and more important.
It really is. Developing energetic materials that are better for the environment is a major driver now.
What are the goals? Is it just about being cleaner?
Not entirely. Yes, reduced environmental impact is key, but they're also looking for higher energy content, making them less vulnerable to accidental ignition.
Safety too.
Right. And improving mechanical properties, reducing their signature, making them harder to detect, and extending their shelf life. It's a multifaceted goal.
So what are some of these new, greener options being looked at?
Well, on the oxidizer side, things like ADN, ammonium dinitramide, HNF, hydrazinium nitroformate, even ammonium ozonide are being developed. They tend to be more powerful and burn cleaner than traditional oxidizers.
On the fuel side.
Energetic binders, polymers like GP, BAMO, or copolymers like BAMO THF, these have the potential to significantly boost a rocket's efficiency, its specific impulse, maybe above 320 seconds according to the source.
That's a pretty big jump. Are there other ways to boost performance with these new materials?
Yeah, the research mentions adding things called energetic plasticizers like tetrazetomalonate or tetrazetoglutarate to increase the energy density. And then there are these fascinating nitrogen-rich compounds being explored, nitroguanidiniumides, theoretical molecules like N8 or N10 potentially offering even higher energy release.
And metals.
Yes, adding metal powders or metal hydrides at the nanoscale, really tiny particles, can significantly crank up the burn rate.
But sounds like there's a caveat.
A big one. The source rightly points out that for many of these new materials, we still need more reliable, comprehensive technical data to fully understand their capabilities, their safety profiles, and how they actually perform in real systems.
Right, lots of potential, but more work needed. Now, a standard ingredient in many solid rockets is ammonium perchlorate, AP. What are its downsides, and what's being looked at to replace it?
AP has been a workhorse, but it does have significant drawbacks. Especially for military use, the huge plume of white smoke it produces is a big problem, makes the missile easy to track.
And interferes with guidance.
It can, yeah. It can affect optical or radar guidance systems, so there's a strong push towards smoke-reduced or smokeless propellants.
But finding a replacement for AP isn't straightforward.
Not at all. Finding something that matches its performance, cost, and stability is tough.
So what are the main contenders?
Okay, one is ammonium nitrate, AN. It's cheap, has a good oxygen balance for burning,
Right.
but it absorbs moisture easily, which is bad. And its burning rate can be unpredictable because it exists in different crystal forms or polymorphs. Stabilizing it might help prevent cracking, but generally its energy is lower than AP-based propellants.
Okay, what else?
Then there's ADN, ammonium nitramide, very high oxygen balance, which is great, but it's not very thermally stable, and it's still quite expensive to make.
Hmm.
Any others?
Hydrozinium nitroformate, HNF,
Mm-hmm.
high energy, burns fast, very efficient combustion. Sounds good, right?
Yeah.
But again, low thermal stability. It's also sensitive to friction, and there's a concern about potentially releasing carcinogenic hydrazine gas.
Not ideal. And finally, hydroxylammonium salts, like HAN. They can boost the oxygen content. But there are worries about releasing hydroxylamine, which might have mutagenic effects, potentially altering DNA.
Wow. So it's a real balancing act.
It is. Right now, there isn't a perfect fielded alternative to AP. That's why there's so much research focused on finding better oxidizers, or at least ways to reduce the amount of AP needed in formulations.
A complex chemical puzzle indeed. Let's shift now to how these materials actually burn. The research you sent has some interesting comparisons.
Yeah, there's data looking at surface temperature versus pressure for different compounds like BT8s, DHT, and the well-known HMX.
What does that tell us?
It shows how their burning behavior changes under pressure. Some burn faster as pressure increases, others might level off. Interestingly, the actual flame temperatures measured can sometimes be lower than the theoretical maximum.
Why is that?
It's because some of the intermediate products formed in the flame are themselves very high in energy, so not all the energy is released as heat immediately.
And where does the main reaction happen for some of these?
For materials like DHT and BT8s, thermocouple measurements suggest that the reactions happening in the solid or liquid phase, right near the surface, are really dominant in driving the overall combustion process.
The source also mentioned it's tough to measure temperatures for really fast-burning stuff.
That's right. Things like tetrazines burn incredibly fast. Getting accurate temperature profiles, even with tiny sensors, is really challenging.
Is there a general rule?
The assumption generally is that materials burning faster tend to be less thermally stable. There's often a trade-off.
What about these CHNO tetrazines mentioned? They sounded potentially powerful.
They're interesting compounds. They combine a ring structure, the tetrazine cycle, which actually absorbs heat when it forms,
Right.
with nitroamino groups that pack a lot of oxygen and release energy when they decompose. This combination, theoretically, leads to high-performance detonation velocities comparable to standard explosives like RDX and HMX, even if their total energy content might be a bit lower.
We also saw that measurements of burning rates for some compounds, like TAG2NQ2Ts and NQ22Ts, varied between labs. Why would that happen?
Yeah, the source flags that. It likely comes down to variations in the purity of the material samples tested.
Quality control.
Exactly. And also subtle differences in how the samples were prepared and how the tests were actually run. It really highlights the need for standardized procedures and well-characterized materials to get reliable, comparable data.
Makes sense.
Yeah.
And this TAG2NQ2Ts seem to decompose differently.
Yes, it's noted as being less thermally stable than NQ2Ps. When it breaks down from heat, its decomposition speeds up over time. That's called autocatalysis.
Yeah.
And looking at the gases produced, it seems the tag part of the molecule plays a big role in how it decomposes, leading to large amounts of ammonia gas being formed.
Interesting specifics. Okay, let's focus on one particular ingredient that gets a lot of attention.
Yeah.
Nanosize aluminum, or NAL.
Right now, there's been a lot of buzz around it.
Why the focus on nanoaluminum?
Well, conventional larger aluminum powders haven't really been that effective in boosting burn rates in solid propellants or the regression rate how fast the fuel burns back in hybrid rockets.
Because people looked smaller.
Exactly. The focus shifted to these much, much finer nanoaluminum particles and also to aluminum that's been activated either chemically or mechanically, and boron compounds too.
But going nano isn't without problems, is it?
Definitely not. A major headache with Al is oxidation. It reacts very readily with air, forming an oxide shell.
Like rust on iron.
Sort of, but it's an aluminum oxide layer. And for really small particles, say under 20 nanometers, that oxide shell can actually make up a significant chunk of the particle's total mass.
And that's bad because...
Because the oxide doesn't release nearly as much energy as pure aluminum when it burns. Plus, that shell increases the temperature needed to even get the particle to ignite. It reduces energy and makes it harder to light.
So how are researchers getting around this, protecting the nanoparticles?
Coating them is the main strategy. The research describes a few methods. One uses perfluorotriticanoic acid.
How's that done?
It involves dispersing the nanoparticles using ultrasound, then stirring them in this acid solution, all under a nitrogen atmosphere to prevent oxidation during the process.
Okay. Any other coatings?
Oleic acid is another common one. They can even confirm the coating is there using techniques like FTIR spectroscopy, which looks for the specific chemical signatures of the coating material on the particle surface.
What do these coated particles look like?
Electron microscopy images show they're generally spherical, similar to the uncoated ones, although sometimes the uncoated powders can clump together into flake-like shapes, and the source notes that sometimes you can even see traces left over from the coating process itself.
Interesting. Okay, let's switch to the actual combustion process in solid propellants. Can you walk us through the main zones or stages?
Sure, it's generally thought of in three main zones. Right at the propellant surface, there's a very thin zone where reactions happen in the condensed phase, the solid or liquid. The temperature shoots up rapidly here to the surface temperature, FTs.
Okay, zone 1, condensed phase. What's next?
Next, moving away from the surface into the gas, you have the gas phase diffusion reaction zone. Here, the gas is coming off the propellant mix and react exothermically releasing heat, and the temperature climbs further towards the maximum flame temperature, Ts.
And the third zone?
That's the luminous flame zone, further out. This is where the combustion reactions essentially go to completion, the final product gases are formed, and the temperature typically reaches its peak.
So it's a layered process. What happens right at that interface where the solid turns into gas? You mentioned AP and HTPB earlier.
Right, so common ingredients like ammonium perchlorate, AP, and the HTPB binder, they transition into gases through decomposition or sublimation.
They don't really mix as solids.
Not really on the burning surface. They decompose and release gases separately, creating this kind of gaseous layer right above the solid.
Okay, then what?
The decomposition products from the AP, which are rich in oxygen, react very close to the surface in what's called a premixed flame. Then further away, these hot AP products and the HTPB decomposition products mix and react through diffusion. That's the diffusion flame zone we mentioned.
And if there's aluminum?
That's where the aluminum combustion happens, typically in that diffusion flame zone further from the surface, reacting with the oxidizer products, generating the final combustion products like aluminum oxide, and releasing a tremendous amount of heat.
Okay, that clarifies the solid side.
Yeah.
Let's switch gears again to liquid and gel propulsion. How does liquid kerosene compare to gelled kerosene in terms of burning efficiency?
Well, the research indicates that for liquid kerosene, the combustion efficiency varies depending on the mixture ratio, the equivalence ratio, how much fuel versus oxidizer you have.
And the gelled version?
Gelled kerosene generally shows lower combustion efficiency compared to its liquid counterpart.
Why is that?
The likely reason is lower combustion temperatures when using the gel. The gelling agent itself might interfere slightly, or the way it atomizes isn't as efficient.
Can that be improved?
Potentially, yes. The source suggests a few avenues. Choosing better gelling agents, developing improved atomizers specifically designed for gels, and optimizing the geometry of the combustion chamber itself to promote better mixing and burning of the gelled fuel droplets.
Okay. The papers also talk about condensed combustion products, CCPs, forming layers on burning metal particles and affecting how they clump together, or agglomerate. Sounds complicated.
It is quite detailed physics and chemistry happening there. They describe two main classes of these surface layers that form on the burning metal particles.
Class A.
Class A is described as like a carbonaceous skeleton structure with the pores filled with metal and metal oxide. In this scenario, if more of the metal burns heterogeneously reacting directly with the surrounding gas, you end up with more oxide within these clumps.
And that matters because?
It leads to stronger adhesive forces between the particles, making the final agglomerates larger, which can hurt performance.
In Class B?
Class B is more like a metal skeleton formed from the initial metal particles themselves.
Does the oxidizer play a role here?
Yes, the type and size of the oxidizer particles influence this too. If the oxidizer particles kind of melt and fuse together into a continuous layer, it changes how these CCP surface layers form within the gaps between the metal particles.
Very intricate interactions. Now let's explore using dual oxidizers and energetic binders in solid propellants. Combining ingredients seems to offer some benefits.
Absolutely. Synergistic effects are definitely possible. One really interesting example highlighted is the interaction between AP and HMX.
How do they interact?
It turns out that the temperature at which HMX starts to thermally decompose is actually influenced by the ratio of HMX to AP in the mix. Yeah. At certain ratios, the source mentions between 40 and 90% HMX, you can get both the HMX and the AP decomposing simultaneously, but at a lower temperature than either would alone. And it happens with more heat release and a faster overall mass loss.
That sounds very beneficial.
It can be, but there's a catch. The size of the AP particles matters. Larger AP particles seem to reduce this synergistic effect. It highlights how important the surface area of the AP is for these interactions.
And how does mixing HMX AP affect the overall burning rate?
Studies looking at HMX combined with active, energetic binders show that adding these HMX-AP mixtures generally increases the burning rate compared to just the binder alone.
Is there a way to optimize this?
Well, intriguingly, the research suggests that if you coat the HMX particles with AP, you can achieve similar burning rate characteristics, how it changes with pressure as using simple powdered mixtures, but potentially with much less AP overall.
That could be advantageous. There was also a mention of how the curvature of the burning surface affects the burn rate. That seems subtle.
It is, but it's a real physical effect. Combustion models predict there's actually a limit, a critical curvature beyond which self-sustained burning just can't happen.
And that explains.
It helps explain phenomena like the critical combustion diameter, the minimum size a piece of homogeneous energetic material needs to be to sustain its own burning.
Fascinating. And finally, in this area, these combustion models for energetic binder mixtures, what are they used for?
These models are trying to capture the complexity. They consider things like the curvature of the thin binder layer between filler particles and the time it takes for those filler particles, whether they're inert like silica or active like HMX, AP, or Cl20, to actually ignite.
Did they match experiments?
They compare the model predictions to experimental results using these different fillers. This helps understand how factors like particle size, concentration, and the binder's own burn rate interact.
Any key findings?
One interesting outcome is finding a sort of unified relationship for the ignition delay of HMX, AP, and Cl20 particles. It seems to depend consistently on their size, the overall mixture burning rate, and the thickness of that binder layer around them.
Why is that important?
Because that ignition delay is crucial in determining the overall burning rate of the entire mixture. These models ultimately allow calculation of things like temperature sensitivity and the pressure exponent key parameters for predicting propellant performance.
Okay, building on that idea of multiple oxidizers, let's talk specifically about dual oxidizer composite solid propellants. Why use two oxidizers?
The main driver is performance enhancement. You're aiming to increase both the gravimetric-specific impulse thrust per unit weight of propellant used per second and the density-specific impulse, which relates to thrust per unit volume.
How do you achieve that?
By incorporating highly energetic materials alongside the primary oxidizer. Things like Cl20, HMX, ADN, or GUDN are often considered.
But adding them isn't simple, right?
No, it's a trade-off. Adding these high-energy ingredients can definitely affect other critical properties, the combustion behavior, sensitivity to ignition, mechanical properties, and even the final specific impulse achieved. It needs careful formulation.
Can you remind us of the key features of those energetic oxidizers?
Cl20.
Cl20 is known for very high energy density and producing less smoke, which is good for low observability.
HMX.
HMX also has high energy potential, can burn smokelessly, but its combustion can be quite complex to predict and control.
GUDN.
GUDN offers high detonation velocity, generally good sensitivity and stability characteristics, along with high energy.
And ADN.
ADN is attractive for its clean combustion products and high heat of formation, meaning lots of energy release. But there are ongoing challenges related to its stability and cost, as we touched on earlier.
How do researchers actually measure the burning rate of these complex propellant?
A common method described is using a chimney-type strand burner.
How does that work? You take a small, thin strand of the propellant. It's ignited, often using an alternating electrical voltage applied to a wire. Then, fine fuse wires are embedded at precisely known distances along the strand.
And you time them melting.
Exactly. As the burning surface reaches each fuse wire, the wire melts, breaking an electrical circuit. By timing when each wire melts, you can calculate the steady burning rate very accurately.
Clever. And what did the tests show for propellants using both AP and ADN?
The research confirmed that these AP-based dual oxidizer propellants could be successfully manufactured using standard vacuum casting techniques and that they burn steadily.
Any differences in burning?
Most formulations showed pretty similar burning rate responses to pressure. However, the specific combination of AP and ADN resulted in a noticeably higher burning rate and increased sensitivity to pressure changes.
And particle size mattered.
Yes, interestingly, for the AP-ADN propellants, using larger particles of ADN actually led to an increase in the pressure exponent, meaning the burning rate became even more sensitive to pressure changes.
Interesting detail.
Yeah.
Okay, let's shift focus geographically now and look at some specific national efforts. Russia has such a long and impressive history in rocket engines. What are some highlights?
Oh, absolutely. Russia has been responsible for some truly pioneering technologies over the past 50 years or so.
Like what?
Well, they developed the first engines using what's called a full-flow staged combustion cycle with storable propellants that can be kept liquid at room temperature. The RD-270 was a key example.
Staged combustion. That's highly efficient, right?
Very efficient. They also built the RD-170, which is still the highest thrust engine ever flown, using an oxygen-rich staged combustion cycle with liquid oxygen, LOX, and kerosene. Just immense power.
What about hydrogen engines?
They developed the RD-57, a LOX liquid hydrogen LH2 staged combustion engine that innovatively used both propellants for cooling different parts of the engine. And the RD-0120, used on the Energia core stage, was another advanced LOX LH2 engine with a fuel-rich staged combustion cycle.
Any other unique designs?
Yes, the NK-33. It's a high-pressure, oxygen-rich LOX kerosene engine, notable for operating without baffles or cavities inside the main combustion chamber, which were typically used to suppress instabilities. A very clean internal design.
It's amazing that engines designed decades ago, like the RD-107 for Soyuz and the RD-275 for Proton, which were derived from their early efforts, are still flying today.
It speaks to the robustness and effectiveness of those original designs. The RD-170 in particular is just a powerhouse. Its injection head design, the way it mixes propellants, is incredibly sophisticated.
The others you mentioned.
The RD-57's cryogenic injector element, using clever fluid dynamics, is notable, and the NK-33's turbopump, with its concentric shafts letting the oxygen and kerosene pumps spin at different optimal speeds, is another example of really clever Russian engineering.
The Energia system, using those RD-170 boosters and RD-0120 core engines, really showcased this technology, didn't it?
It absolutely did. That was the pinnacle of their heavy lift capability. And the RD-171 variant, adapted for the Zenit launcher, shows how these core technologies could be repurposed.
Okay, let's hop over to Japan. They're putting effort into liquefied natural gas, LNG, as a rocket fuel. What's the appeal of LNG?
LNG, which is mostly methane, does offer some potential pluses. Compared to, say, liquid hydrogen, it's easier and potentially cheaper to store for longer periods. It's also denser than hydrogen and non-toxic, unlike some storable propellants.
Sounds promising.
Yeah.
So why aren't we seeing LNG rockets flying routinely?
Well, despite the advantages and ongoing R&D in Japan and elsewhere, no LNG-fueled rocket engine has actually made it to operational flight yet.
What's the main hurdle? Performance.
That seems to be the key issue right now. The specific impulse, the efficiency measure of current Japanese LNG engines, is cited as being between 310 and 350 seconds.
And that's not enough.
It's good, but it falls short of the target, often considered to be around 360 seconds or higher, especially for applications like reusable boosters, where maximum efficiency is crucial to make the economics work. So closing that performance gap is the big focus.
What kind of R&D are they doing to bridge that gap?
They're working on improving combustion efficiency. The source mentions progress, showing better performance in a smaller 30 kN test engine compared to an older, larger 100 kN engine.
What about cooling the engine? That's always critical.
Right. They're looking at the trade-offs between ablative cooling, where a material burns away to absorb heat, simpler but less efficient, and regenerative cooling, where the fuel flows through channels in the chamber wall.
Yeah.
It seems they might be hitting limits on how much more performance they can squeeze out of ablative cooling. So future plans involve more simulation and high-pressure combustion experiments, testing various injector designs to really optimize how the LNG and oxygen mix and burn.
And the cooling channels themselves.
They're also carefully verifying the heat transfer in those regenerative cooling passages. They found that standard calculation methods like the Bart's equation weren't perfectly matching their results, so they're exploring other ways to get more accurate heat transfer predictions.
Makes sense. Now, JAXA, the Japanese Space Agency, is doing broader work on spacecraft propulsion too, beyond just LNG engines, right?
Yes, absolutely. Their focus is generally on improving performance and reliability across the board,
Such as?
developing thrusters with longer operational lives, creating new lightweight propellant tanks using composite materials, and researching propellants that offer high performance but are less toxic than traditional options like hydrazine.
Can you give some examples?
Sure. They've developed long-life, high-reliability 1 Newton and 4 Newton thrusters using hydrazine monopropellant. These are crucial for attitude and orbit control on satellites like ALOS-2 and GCM-W1.
How do they ensure reliability?
They incorporate redundancy into the thruster design, and the hydrazine is stored in special tanks that use surface tension to manage the fuel, pressurized by helium gas.
Any other examples?
Their Selene lunar orbiter, Kaguya, actually used a bipropellant system N2H4 and MON3, which offered better performance than the MNH-MON3 combination, often used previously in Japan. They've also developed a second generation of their 4N thruster, already flown on the Asnaro satellite.
And they test these extensively.
Oh yes, they do long endurance firing tests to really understand how the catalyst bed inside the thruster degrades over time, depending on how it's fired, short pulses versus long burns.
And the low toxicity propellant research.
Right, they're actively researching a monopropellant called SHP-163. It's a mixture based on HNAN, ammonium nitrate, AN, and water. The goal is a potential replacement for hydrazine.
Is it much safer?
Toxicity data presented shows it's significantly less toxic than hydrazine, closer to things like ADN or even table salt based on LD50 values. They're also doing safety tests, like evaluating its detonability in steel tubes under various mixture ratios to ensure it can be handled safely.
Okay, let's move to gel propellants. The idea of gelling liquids has been around. What sparked the initial interest?
Back in the late 80s, early 90s, there was research suggesting that using gelled propellants, or maybe metallized or cryogenic ones, could offer significant savings in the total launch mass needed for future space missions. That potential for higher efficiency really kicked off a lot of R&D.
And what areas has that R&D covered since then?
Pretty much everything. How to formulate the gels, how to process them, their performance characteristics, how they burn, how they atomize, break into droplets, their flow behavior or rheology, and even the design and testing of engines specifically built to run on various gelled fuel systems. There have been advancements building on early flight tests by companies like TRW and Bayern Chemie.
What have we learned about how these gels actually behave?
Well, studies on their rheology, how they flow using gels like UDMH-MC, show that their viscosity, their stickiness, and their yield stress, the force needed to get them flowing, are strongly dependent on temperature.
And adding metals.
Research has looked at how adding aluminum or magnesium powder affects that yield stress. They've also done experiments forcing the gel through narrow tubes, capillaries, to understand how the flow rate changes with the pressure applied.
Sounds like progress, but are there still hurdles with gel propellants?
Oh, definitely. Several significant ones remain.
Like what?
A key one is that the gelling agents themselves almost always cause a slight performance hit compared to the base liquid propellants, especially if you gel both the fuel and the oxidizer.
Okay, what else?
We haven't really found gelling agents that are both highly energetic themselves and effective at very low concentrations. Also, the properties of gels can change over time or with temperature variations, which raises concerns about storage stability and predictable performance.
Any other issues?
Yeah, getting the gel to flow completely out of the tank's propellant transfer and utilization can be tricky. And as we touched on, their combustion and flow characteristics, especially with metal additives, are more complex than liquids, requiring careful engine design for good atomization and efficient burning.
Right. Okay, let's turn to hybrid propulsion. Japan seems keen on this for potentially cheaper launches, especially for smaller satellites.
Yes, they see hybrids as a promising path towards safer and more economical launchers. They've even used computational tools to explore optimized launch system designs based on hybrid stages for typical small satellite missions.
What technologies are they developing to support this?
Quite a few key areas. Better understanding the fundamental boundary layer combustion over the solid fuel surface, using swirling oxidizer flows to enhance mixing and burning, improving how liquid oxygen is vaporized before injection, developing multi-section swirl injectors, investigating thermoplastic fuels that melt readily, even exploring ways to control both thrust and the oxidizer-to-fuel ratio simultaneously by varying the swirl intensity. CFD simulations are also a big part of understanding the internal flow and combustion.
How do hybrids actually work, fundamentally?
It's a combination, right? You have a solid fuel grain, and you flow a liquid or gaseous oxidizer over or through it. The combustion happens in a boundary layer right above the fuel surface.
And the speed it burns.
That's the fuel regression rate, how fast that solid fuel surface recedes. It's primarily driven by the heat fed back from the flame to the fuel surface.
What's the traditional challenge with that regression rate?
Historically, it's been relatively slow compared to solid propellants and also harder to predict and control accurately.
So how are researchers trying to boost it?
Several approaches are being pursued. Multi-port grains, fuel grains with multiple channels increase the surface area but can get complex for high-thrust engines.
What about fuel types?
Using fuels that liquefy easily on the surface, like paraffin wax, is a major focus. These can achieve regression rates several times higher than traditional rubber-based fuels like HTPB, because tiny droplets of molten fuel get entrained in the flow.
And the swirling oxidizer.
Right, injecting the oxidizer with a swirl, sometimes called vortex flow or soft hybrids, enhances mixing and heat transfer, which also significantly boosts the fuel regression rate. Research is ongoing to understand exactly how the rate varies along the fuel grain with these swirling flows.
Combustion instability is always a concern. What about in hybrids? Japan has studied low-frequency instability, LFI.
Yes, LFI is a known issue in hybrids. Experiments have looked at how things like the oxidizer injection method, the chamber pressure, adding diaphragms at the rear end of the fuel grain, or using backward-facing steps in the chamber geometry affect these low-frequency pressure oscillations.
What causes LFI?
One leading theory, supported by the Japanese research, involves vortex shedding in the post-chamber, the volume after the main fuel grain. Swirling pockets of gas, potentially containing unburnt fuel and oxidizer, can shed periodically into this region.
And then?
This shedding can lead to unsteady heat release as combustion continues downstream, causing pressure fluctuations. If these fluctuations couple with other processes, like the thermal response of the solid fuel, they can amplify into significant LFI.
There was also mention of injecting oxidizer through the wall and how that affects turbulence near the fuel.
Right, wall injection. CFD simulations showed this significantly alters the turbulent flow structures near the fuel surface. Instead of the typical elongated streamwise vortices you see without wall injection, wall injection tends to create more tilted, hairpin-like vortices, leaving different footprint patterns on the fuel. This change in near-wall turbulence can directly impact heat transfer and fuel vaporization, and thus the regression rate.
And finally, for Japan's hybrid work, experiments comparing paraffin and HTPB fuels under simulated engine conditions.
Yes. The goal there was really about structural integrity and melting performance. Subjecting fuel samples to representative high pressures and heat fluxes lets researchers see how they hold up. Do they melt too much? Do they slump? Do they maintain their shape? It's crucial for ensuring the fuel grain performs predictably in a real engine.
Okay, moving beyond Japan, other research focuses on hybrid combustion, especially paraffin fuels. What's being found?
Studies are analyzing the ballistic response, basically, the regression rate of both HTPB and paraffin fuels under steady and transient conditions, always aiming for enhancement.
Any success with HTPB?
Adding coated nanoaluminum to HTPB showed promise. It made the regression rate less sensitive to changes in the oxidizer flow rate and gave a significant boost overall.
And the waxes?
Solid wax fuels, certain paraffins, showed even larger increases in regression rate. That entrainment mechanism is powerful, but the downside is their poor mechanical strength. They're soft.
How are they trying to fix that?
By blending the wax with thermoplastic polymers like CBSMA and adding things like carbon black, the goal is to toughen up the fuel matrix while hopefully retaining that high regression rate driven by fuel entrainment. It's about finding the right balance between mechanical properties and burning performance.
What about analyzing these fuels thermally, using techniques like DSC?
Differential scanning calorimetry, yeah. It measures heat flow into or out of a sample as its temperature changes. It helps identify melting points, decomposition temperatures, and the energy involved in those transitions.
What did it show for the paraffin waxes and blends?
It confirmed the melting ranges for different waxes. Adding the thermoplastic polymer generally only caused small shifts in those melting peaks. Interestingly, reducing the amount of wax in the blend seemed to lower the heat release during decomposition, possibly because the polymer network restricts the paraffin molecules, requiring higher temperatures to fully break down.
And how do these fuels respond to rapid changes, like throttling the engine down?
Transient combustion tests, where the oxidizer flow to an HTPB fuel was decreased rapidly, showed the regression rate didn't just smoothly follow the flow reduction.
No. What happened?
There were faint oscillations observed in the regression rate. This is likely due to thermal lag, the time it takes for the temperature change caused by the reduced oxidizer flow to actually penetrate into the solid fuel and affect the surface burning.
Okay, let's bring NASA into the picture. They obviously have a big roadmap for chemical propulsion tech.
Yeah.
What are their overarching goals?
NASA's roadmap is about driving improvements across the board. They want higher thrust, better specific impulse, efficiency, more power, lower system mass.
The usual suspects.
Right, but also reduced complexity, easier manufacturability, and improved durability and reliability. Basically, making chemical propulsion better, cheaper, and more robust for future missions.
They talk about mission pull versus technology push. What's the distinction?
Mission pull means developing technologies specifically because they are necessary for planned NASA missions. We need this capability to do Mission X.
And technology push.
That's about developing potentially game-changing technologies or alternative propulsion systems that aren't strictly required for current plans, but could enable totally new kinds of missions or offer significant advantages in the future, pushing the boundaries beyond immediate needs.
What are some specific technical hurdles NASA is tackling?
One mention is the challenge of safely scaling up propellants that are sensitive to shock. How do you handle larger quantities safely? Their plan involves research into desensitizing additives.
Make sense? Any others?
Developing and maturing high-speed engine concepts, like those based on rapid deflagration or even detonation waves, rotating detonation engines, for example. The roadmap includes work on component development, ground testing, and validating these advanced concepts.
Now, the space landscape is changing with commercial players like SpaceX, Boeing, etc. How does that influence propulsion needs?
It's definitely driving demand. You have commercial cargo and crew flights to the ISS needing reliable, cost-effective propulsion. You have plans for much larger launchers like Starship requiring engines with immense thrust and reusability.
And space tourism.
Right. Ventures like Virgin Galactic also need advanced chemical propulsion, maybe higher specific impulse for suborbital hops or reaching orbit, perhaps higher density propellants for compact first stages. The commercial market adds new pressures and opportunities for innovation.
Okay, let's briefly touch on a more niche concept. Laser-assisted chemical propulsion microthrusters, LACPM. Tiny thrusters boosted by lasers.
That's the core idea. Use laser irradiation to enhance or control the combustion of a solid propellant in a very small thruster, potentially for precise spacecraft control.
How does the laser help?
The equations presented show that the thrust and specific impulse depend directly on the laser's radiant flux, how much power hits the surface, and a property called the radiation sensitivity coefficient, which describes how much the propellant's burning is affected by the light.
So more laser power means more thrust.
Generally, yes, up to a point. The relationship gets simpler in vacuum. If the propellant wouldn't burn at all without the laser, one term in the equation simplifies. Essentially, laser power and propellant sensitivity dictate the performance.
Interesting concept. Okay, we have a few more specialized topics from the sources.
Right.
One is about synthesizing Cl-20, that high-energy material.
Yes, the research described focused on one specific chemical step in a known synthesis route, the hydrodebenzylation of a precursor molecule called HBIW to another called TADBDW.
Using a catalyst.
Right, using a specific potassium-vanadium catalyst on a carbon support called subunit. They studied how the catalyst's active sites could get blocked or deactivated during the reaction.
What did they find?
They found that the highest yield of the desired product, TABBW, was actually achieved when they used more hydrogen gas than theoretically required by the reaction stoichiometry, over 120%.
More hydrogen help.
Up to a point. They also saw that using too much hydrogen, beyond about 110% of stoichiometry, started to decrease the catalyst's specific surface area. And they noted that a different common catalyst, palladium on carbon, wasn't very effective for this step when they tried to reuse it.
Very specific chemistry. Now, a critically important topic, environmental impact and safe disposal.
Hugely important, and getting more attention all the time. There's a clear push to manage the environmental footprint.
Oh.
Two main ways. Developing new, inherently greener materials and better understanding the existing ones, their toxicology, their impact on ecosystems and human health, how they aged, their vulnerability.
Just cost a factor.
Always. Cost-effectiveness is key. This might sometimes favor using existing, well-understood materials but specifying their use and disposal more carefully rather than always opting for expensive new ones.
And life cycle management comes back in.
Absolutely. Understanding the whole chain, material characteristics, manufacturing, in-service use, degradation, and final disposal is essential for proper risk management.
How do they assess propellant aging?
Various analytical techniques are used. Gas chromatography, GC, can detect volatile breakdown products. Differential scanning calorimetry, DSC, can see changes in thermal stability. Tensile testing measures changes in mechanical strength and flexibility. NMR spectroscopy can probe molecular changes.
Any other techniques?
Dynamic mechanical analysis, DMA, in torsion mode was mentioned for studying HTP BLAP propellants. Changes in how the material absorbs energy, the tan delta curve, indicate changes in stiffness, often due to oxidation of the binder. Hardness testing is another simpler method to track changes due to cross-linking, plasticizer migration, or moisture uptake.
And checking inside a motor without cutting it open.
Non-destructive techniques like 3D computed tomography, CT scanning, are invaluable for assessing the internal structure and integrity of rocket motors for defects or aging effects.
Okay. We also saw research on energetic binders like GAP and desmorphin used with ADN oxidizer. How do they compare to traditional HTP-BAP?
This research specifically looked at formulations using those binders with ADN. One immediate difference noted was that you generally can't pack as high a percentage of solids, ADN, and fuel into these binders compared to HTPB.
Why not?
It's partly due to the needle-like crystal shape of standard ADN, which doesn't pack efficiently. That's why prilling ADN, processing it into more rounded particles, is often done to improve packing density.
What about performance?
The study found that the ballistic properties, like burning rate, were more strongly influenced by the type of oxidizer used, ADN versus AP, and the particle size distribution, rather than the amount of metal fuel added.
And they use those EMG functions again.
Yes, they applied those energetic material genome functions to model the DMA results, the loss factor curves, for these different formulations. This helps connect the macroscopic mechanical behavior back to the underlying molecular transitions and energy dissipation processes within the material.
Interesting application. Finally, let's cover HAN-based liquid propellants for thrusters and some lessons learned.
HAN, hydroxylammonium nitrate, is attractive but tricky. Its high burning rate, even at low pressures, means the composition needs careful tuning for thruster control.
Can it use standard catalysts?
It can be decomposed using catalysts like iridium and platinum, similar to hydrazine. However, for good pulse mode performance, quick on-off bursts, and long operational life, there's a need for catalysts that are more active at lower temperatures and can better withstand the heat cycles.
What are the key safety lessons from testing HAN thrusters like SHP-163?
A major one is the critical need to prevent propellant accumulation in the catalyst bed, which could lead to an explosion. This requires careful control of the bed temperature and monitoring it at multiple points to ensure decomposition starts promptly and smoothly.
Any other precautions?
Verification tests simulating the conditions within the propellant feed lines have also been conducted to investigate potential causes of past incidents and ensure a safe system design.
Okay, now for something completely different but fascinating. Those optical phenomena in the upper atmosphere after launches. What's going on there?
It's pretty dramatic physics. When a rocket nozzle is underexpanded at high altitudes, meaning the exhaust pressure is much higher than the very thin atmospheric pressure, the exhaust gases expand explosively outwards.
Like a Sean wave.
Exactly. Strong shock waves propagate into the surrounding atmosphere, causing the combustion products to spread out rapidly perpendicular to the rocket's motion at speeds potentially reaching 3 to 5 kilometers per second.
That's incredibly fast. How much material are we talking about?
It can be substantial, potentially several hundred kilograms of exhaust products injected, depending on the engine's chamber pressure, volume, temperature, and the specific gases produced.
And these clouds expand.
Yes, these expanding clouds of gas and sometimes dust can reach transverse sizes of around 1,000 kilometers. Some fragments can even get thrown upwards to altitudes around 700 kilometers if they have high initial vertical velocities.
How long do these effects last?
The overall development time is mostly governed by how long it takes for the material to rise and then eventually settle back down to the turbopause boundary around 100-kilometer altitude. The sources even show examples of gas-dust cloud evolution after stage separation or from injected monomethyl hydrazine fuel at high altitudes.
Amazing scale. Lastly, let's briefly touch on green technologies for disposing of energetic materials when they're no longer needed.
Right, closing the loop. Bioremediation is a key area here.
Using microbes.
Exactly. Using microorganisms, bacteria, fungi, to naturally break down explosives and propellant ingredients in contaminated soil and water. They essentially eat the contaminants.
How does it work chemically?
The microbes use various biochemical pathways, often involving reduction or oxidation reactions, to degrade the energetic compounds into less harmful substances.
Are specific microbes being studied?
Yes, research has identified specific bacterial strains like Raoul teletergena, ST famarium, and Micrococcus species that are effective at removing TNT and related nitrotoluene compounds. Techniques like immobilizing the microbial cells onto supports are also being explored to make the degradation process more efficient and potentially allow the treatment system to be reused.
Okay. Wow, we covered a lot of ground. We also had sources touching on challenges in manufacturing large, solid boosters, like India's S-200.
Details on reusable rocket engine technologies, looking at component life, cooling, coatings.
Even civilian uses of solid propellants, like hail suppression rockets and fire extinguishers.
The chemistry inside car airbag gas generators.
And using upper stages, maybe with hybrid propulsion, for active space debris removal. Lots of fascinating areas we unfortunately just don't have time to delve into today.
Absolutely true. But it's clear from the breadth of material you provided just how much research, development, and innovation is happening across the entire spectrum of chemical rocket propulsion. It's a dynamic field.
Definitely. Okay, let's try to quickly sum up the key takeaways. Chemical rocket propulsion is, well, complex. There's constant innovation happening, from the energetic materials themselves to different propellant types, engine designs, safety protocols, and a growing focus on environmental aspects.
Yeah, we've touched on everything from nano-engineered materials and advanced combustion modeling
To reusable engine technologies, greener alternatives, and even safe disposal methods.
We really hope this deep dive has given you a valuable, condensed overview, a shortcut, if you will, to understanding the key insights from the diverse sources you shared on this multifaceted world.
But as we said, this really is just scratching the surface, isn't it?
Oh, absolutely. Each one of these topics could be its own deep dive. There's so much more detail and ongoing work. We definitely encourage you to explore further any areas that particularly caught your interest.
So, a final thought, perhaps.
Well, it's clear that as humanity continues to push the frontiers of space exploration, and as we find new terrestrial applications for these powerful technologies, the innovation and the fundamental understanding within chemical rocket propulsion will remain absolutely critical. It's going to keep playing a vital role.